So let's take a look at what's given here. Let's say that this is a hockey puck. Let me make it look round here. Oh, that's better. Okay. A hockey puck's going to be hit by a hockey stick, and the hockey stick's going to provide a constant 4.5 Newton force to the hockey puck. Let's say it's on ice, so there's no friction, and this force is applied through a displacement of 0.15 meters in this direction. We want to know how much work was done and what was the change in kinetic energy of the hockey puck. Okay, so whenever you want to know how much work was done by a force, okay, work, which is the transfer of energy. Look, here's a hockey player, and a hockey player's got a lot of energy, and they're applying a force to the hockey puck through a displacement. They are transferring energy from their arms through the stick into the puck, giving the puck kinetic energy. Okay, well, the work is force dotted with displacement, which is delta x. Now I put the dot in there just to, be thorough, but you can see that the force and the displacement are in the same direction. So this just becomes force times displacement. The magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. But what's the angle between to the right and to the right? 0. And the cosine of 0 is 1. So this force is just 4.5 newtons times 0.15 meters. And when you plug that into your calculator, you should get 0, if you round it off, 0.68 joules. Which isn't very much, really. But, hey, the hockey player transferred this much energy out of his body and into the puck. Now, that happens because we're going to consider this the net force acting on the puck. I mean, look at this puck. Yeah, there's gravity, it's pulling it down. Yeah, there's a normal force pushing it up. But we're saying, hey, there's no friction here. Let me ask you this. Why does the normal force not do any work? How come the normal force doesn't do any work on the puck as it slides across the ice? Huh? Yeah, it's not in the same direction as the force. Or you could say this, the force has no component in the same direction. I'm sorry, this force has no component in the same direction as the displacement. Or you can say, the work done by the normal force would be the normal force times the displacement times what? The cosine of, and what's the angle between this force and this displacement? 90 degrees. What's the cosine of 90 degrees?
0.
In most countries, it's 0, yes. And so, no work is done. And the same thing is true with gravity. If you try to figure out the work done by gravity, the force of gravity times delta x times it's the cosine of 90 degrees that makes the whole thing 0. So these two forces don't do any work. This is the net force, it does work. And because that's the net force and it's doing work, the change in kinetic energy for the puck is also 0.68 joules by the work energy theorem. And there you go.